Hey scholars, it's good to be back with you. This is another in a series of videos about statics, and today I'd like to talk to you about how to add force vectors. Now this is something we see a lot in statics problems because we see this a lot in the world outside the classroom. So it's good to know how to do this. First thing we need is a practice example. So I made a little triangular structural element here, and it's pinned at the left two corners there and there. And let's put two forces coming off of it. So let's have 100 newtons coming off at an angle of 20 degrees to the horizontal, and let's have 200 newtons coming off at 60 degrees to the horizontal. Okay, so that's 60 degrees with respect to the horizontal. Now, in order to figure out what's going on, we've got to resolve these two forces into a single one. Well, there's a couple of ways to do this. One, possibility number one, is to just add the components. And number two is to start doing some trig. Basically, it's called the law of cosines is what we'll use here. Use the law of cosine, see how that works. They both give you the same answer. They both work just fine. So first let's add components. Let's see how that works. Well, in order to solve this problem, we're going to want to sum forces in the two directions and some moments. That's the recipe for solving a statics problem. So we're going to need a coordinate system. Let's make that our coordinate system. Okay, so those are the positive sign conventions. Now, in order to do this, we're eventually going to need the x and y components anyway. Well, let's just do that now. I'm going to call this, because I don't have a lot of imagination here, I'm going to call that force A and that force B, and the resultant I'll call C. All right? So if I want to do this by adding vectors, or adding the components, what I'm going to do is I'm going to break A and B down into their x and y components using force triangles. Well, let's see, let's do the components of A. Okay, there's A's my that first force. Well, let's draw the force triangle here. That's 90 degrees. That'll be 20. I know that's 100 newtons. And again, always keep your units in there, gang. If you have the units correct, the numbers will probably be right. So if the units are right, the numbers will probably come along for the right. So keep that in your calculations. So there's that. Now, this is going to be, I'll call that A sub x and A sub y. Well, looks like A sub y over A must be sine of that angle right there. Let's call that sine. So AY is going to be AY. It's going to be A sine, and what should I call that? So let's go ahead and draw a force triangle. There's 90 degrees. There's A, and that's 100 newtons. And this is, I'll call that theta. That's 20 degrees. Right? This is going to be AX, and this is going to be AY because of our sign convention over there. Well, it looks to me like AY over A equals sine theta, and AX over A must be cosine theta. All right, let's just carry that out here. That means AY is A sine theta, and if you work that out, you get that to be 32.202 newtons. Pretty good so far, yes? So AX is now going to be A cosine theta by using the same logic on our force triangle, and that works out to 93 969 newtons. Got my little cheat sheet over here so I get the numbers correct. So there's AY and AX. Well, okay, got that. I'm going to need BX and BY, and using the same kind of logic, I guess I can write this down here. BX is going to be 100 newtons. A little suspicious that comes out to be a round number, right? That doesn't usually happen. Well, the reason it's happening here is that the cosine of 60 is a half, and a half of that is 200. And I think we can just fit this on the screen here. So BY is 173.205. Well, there you go. That's it. Now let me draw just the point where the forces are acting, okay? And I'll leave my positive coordinate system up there. If I've got 100 and 200, well, and that's A and that's B, well, AX is going to be there, BX is going to be there, yes, and AY is going to be there, and BY is going to be there. So I've broken it down into its components. If I want to know, if I want to start adding these now, it's really easy, isn't it? I could do this graphically. I guess I have to get rid of that, don't I? So that's AX, and that's BX. And if I decide to make the resultant vector C, this is CX. Well, guess how this is going to work. There's AY, and there's BY. Now these aren't to scale because I'm just on my board here. I don't have a piece of graph paper. But this is now CY. But here's the thing. I mostly don't need CX or CY. In order to sum my forces in the X and Y direction, I need AX, BX, AY, and BY. Well, I've got them. I don't need to go to here if I don't want to. Now, if I did, for completeness, if I want to know the magnitude of C, well, C, using the Pythagorean theorem, hang on here, I'm doing this wrong. There we go. CX squared plus CY squared. Okay? Let's just figure out what that is. And it looks like it's going to be 283.975 newtons. Well, if I want to know the direction here, and what did I decide to call that? Gamma, I think, on my notes. If the gamma, the angle at which that force is acting, okay, that's just the inverse tangent of CY over CX. And if you work that out, you get to be, let's see, 46.918 degrees. So far, so good. Now, that's the first way to do this. That's probably the way you're going to want to do this, because we need the components anyway. Well, there's another way to do this that you might have learned in, I don't know, maybe trig class in high school or something, and that's using the law of cosines. Well, we can do that. Let's do that. Now, this one's a little less intuitive because the law of cosines isn't that intuitive. It's true, but how many of us would look at the law of cosines and go, oh yes, that's obvious? Well, not me. And I don't know what that is. That's C. I'm going to figure that out. Well, I already know what it is, 283.975, but let's pretend I don't know that. Now, I need to know that angle in there. Well, that angle is 40 degrees, since this angle is 100 and that angle is 60. So this has to be 140 degrees in there. Well, if I want to know what C is, the law of cosine says C squared equals a squared plus b squared minus 2ab cosine of that angle right there. I got to call that something. I guess I'll just put it in here as 140 degrees. I guess I don't need that. I'm going to solve for c. I want to know what c is. Well, we've almost got it solved anyway. So it's a squared plus b squared minus 2ab cosine 140 degrees. Again, I probably should have given that a name, but I didn't. So when you work that out, guess what you get? You get 283.975. And I did it in both ways on my little cheat sheet here just to make sure it was right. So I got the same answer. Well, the problem now comes, what if I want to know that angle right there? What that angle right there, let's call that maybe delta. Well, I can't find that directly from here. What I've got to do now is I'm going to solve for that little angle in there. I'm starting to run out of Greek letters here. What haven't I used so far? I used gamma. Let's see, I'll call that epsilon. There we go. That little angle in there. Well, I can apply the law of cosines again, making that the opposite and these the two adjacent, and I can back that out. So I can do it this way, and when you do it this way, it's correct. It's mathematically equivalent. So this is the second way to do it. For statics, this probably isn't the most useful one. For statics, you're going to want to break things down into their x and y components, like we did in that first example. So I hope this helps, and we'll talk to you next time.